The article I will focus on is called An Introduction to Multiple Context-Free Grammars for Linguists. It was published by Alexander Clark in 2014. So let's start by saying that, well, we know that some natural language phenomena can be modeled with CFGs, and the most famous one being the cross-serial dependencies attested in Dutch and in Swiss German. And at the same time, we know that context-sensitive grammars may be inadequate to model natural language because they are too powerful in terms of generative capacity. So in 1991, Seki and other researchers come up with MCFGs, which are an extension of CFGs that allows us to work with discontinuous constituents or displaced elements. And this article is called On Multiple Context-Free Grammars. It is on the seminar folder. And MCFGs are mildly context-sensitive grammars, which means that they are between type 1 and type 0 in the Chomsky hierarchy.
0 or 2?
2 between context-free and context-sensitive.
Right.
Yeah,
One
sorry,
and two.
yes. Um, and MCFGs are equivalent to some sort of minimalist grammars, some versions. And well, in his article, Clark provides a non-technical explanation of MCFGs and explain how these can give a natural treatment of the types of syntactic phenomena that in mainstream generative grammar have been treated using movement. Okay, so this won't be a very formal presentation, maybe, but well, I hope it will be helpful anyway. Uh, okay, so the first thing that Clark does is proposing this change in notation, going from this classical notation that he calls top-down to this new quote-unquote notation called bottom-up. Okay, so these rules are equivalent. They define the same language that we are seeing here. Um, and okay, and here, of course, these are terminal symbols. But the blue letters are string variables, while the green letters are constant strings, if we want. Okay, so this bottom-up notation is also known as logical notation because these rules can be regarded as implications, and that is what the arrows are saying. So we have a predicate, and we have a variable in blue, and this rule says basically if a string u is an A and a string b is a B, then a string UV is an S. And these last two rules are equivalent. They are trivial rules. So they only state that they only state that a string A is an A lowercase, so on. So this is how it looks like in a derivation tree. So on the right, we obtain an S after recognizing these two strings, A and B, which are A uppercase and B, and we obtain this maximal projection after applying the rule 1. So this is the value of the variable in this case. Okay, so why do we change the notation? What's the point of it? So first of all, this change is more compatible with the minimalist theory in that the derivation is assumed to be generated bottom up by applications of merge, as we know. But on the other hand, and more importantly, this is helpful because, it helps us manipulate the way in which the yields of two or more constituents are concatenated when they form a more complex constituent. So it is useful to refer to them as variables that satisfy predicates, what the predicate is a non-terminal symbol. So basically, when we say this, we are saying that this string can be derived from the non-terminal symbol through the application of one or more production rules. This is what this means. So in other words, this notation enables us to manipulate the way strings are concatenated in a more explicit way. Well, in CFGs, the order of the strings was implicit. I mean, meaning that the leftmost constituent would surface to the left of the rightmost constituent. But now this doesn't necessarily hold, and that's why we need to specify how the strings will be concatenated. At the same time, Clark establishes the convention that the order of the variables at both sides of the rule remains the same, and this is called linearity. So we have pairs of a string, I mean, ordered pairs of strings. Okay, so let's see which are the MCFG's properties. So their novelty is that they have two-place predicates, which are predicates that apply not only just to one string, but to a pair of strings. And these two strings, as I have said, are ordered, and the number of strings which a predicate applies to is called dimension. Of course, when we say strings, it doesn't actually matter if there are one or more words, as long as they form like a unique phonetical compound that can't be split. So, well, a pair of strings means that there are two strings that may have one or more strings between them. Okay. So I mean, CFGs have rules with only one dimension. That's what make CFGs. But MCFGs technically could include rules with more dimensions, but according to Clark, we don't need them to model natural language. They are not necessary in principle. But I mean, the original formalism uh, allows them. Okay, so in addition to that, we will always want to have some normal predicates like this one, I mean, with dimension 1 to generate full sentences. So at the end of the derivation, we will need a rule that finally concatenates the pair of strings. But this is also possible. So along the derivation, we may also have two-dimension predicates at both sides of the rule, which is obvious. And let's note that in this second rule, some new material is added, meaning that these two predicates are equivalent. And so, as Clark says, this rule is clearly doing something more powerful than a CFG because it is working at the same time on two different chunks of the string, right? And finally, okay, we need this kind of rule, which are the trivial rules, but now with two dimensions. Okay, so a little comment. Okay, now we can no longer express the concatenation with only the order of the symbols at the right-hand side. Well, we just saw this, and but we have to limit ourselves to linear and non-permuting rules. So we have to respect the order of our pairs of strings, right? this is what non-permuting means. Okay, this is a more formal definition provided by Stabler. So we have that multiple content-free grammar consists of a finite non-empty set of vocabulary elements, um, a finite non-empty set of categories where each has dimension greater a greater than 0. So if all the categories have dimension 1, we have a CFG. Okay, these are the strings. Okay, here we may have more than 2-dimension rules, and we can have k strings or k chunks if we want. And well, each chunk belongs to the closure of the union of sigma and x, and each variable occurs at most once on the right and at most once of the left, which is a condition similar, more restrictive, I think, to linearity. And all variables on the left appear on the right. And okay, this is the start category with dimension 1, as we saw. Okay, so we can generate the same language as earlier, as before, with this set of rules. We see an A and a B, then we have an N, but in this case, the strings are not concatenated. We have a comma between them, of course, and that's what we recognize in the second rule. And then this rule adds new strings to the pair already recognized here. And we go like this until we get to the final rule with dimension 1 that concatenates these two strings. But the important thing here is which are the pairs of strings that are derived at the same step. So here they are marked with a subscript, sorry. And if we draw a line between them, I mean, we get these crossed relations. So these are like the strings derived at the same step. The distance is always the same, and this is different to what we had seen with CFGs. So now we have a weak equivalence, but not a strong equivalence, because what we see here would have been impossible with the CFG rules defined before, because, and actually with any CFG, because in this case, the string that is being formed is a unique compound. So we can't place things in the middle of it. We can only place new strings at the sides, on the sides. So well, they have a different structural description. And this is, well, very important because this will help us describe the cross dependency phenomenon. Um, okay, this is a very simple explanation of why MCFG are like in the middle of type 2 and type 1. So what Clark explains is that if we have a valid derivation with a subtree headed with some symbol, whether it is of dimension 1 or 2, we can freely swap that subtree for any other subtree that has the same symbol as its root, and the result will be also a valid derivation. And of course, it doesn't happen. This not always happens with context-sensitive grammars, but it does happen with context-free grammars, right? Okay, so linguistically, as I said, one of the most important strengths of MCFGs that is shared with other mildly context-sensitive grammars is that they can give account of this type of phenomenon, um, where we have a sequence of noun phrases that are marked for either accusative or dative case, and a sequence of verb phrases that require arguments that are marked for either accusative or dative case. And I can either mark the nouns with a different case or alter the position of the nouns without changing the position of its respective verbs either, although this is apparently possible in like the like Swiss German, but Clark in this formalism or in this explanation doesn't rule out this kind of constructions. But it is important to know that these type of constructions are actually grammatical. Um, okay, so what we just have seen is pretty much the way we can deal with cross-dependency constructions as the ones described by Schieber for Swiss German. And the only difference here is that now we have like two different terminal items, and therefore we need to double our recursive role and, well, our terminal rule. But that's the only difference, but formally they are like very similar or identical grammars. And okay, so this is like the final structure. And so what we see is that the symbols that are derived at the same step of the derivation establish now the right dependency. And this is possible because we can like operate with two chunks at the same time, adding material to the left of each of them. And this is possible, as we saw with the CFGs. Okay, so this is another phenomenon that can be expressed through MCFGs. These are the relative clauses where the displaced constituent moves upwards, leaving a trace or a copy. It is irrelevant now. And okay, it is interpreted semantically in the lower position and pronounced in the higher one, right? And this analysis is pretty much the standard analysis, um, where I mean within the generative tradition, um, where the relative clause is attached to the noun phrase, and then the noun would like bind an operator that moves from the original position to the specifier of the complementizer phrase. And but okay, this one is a simplified version, but the core of the analysis doesn't change. And okay, so let's see how movement looks like now here with MCFGs. So first, we have to derive the element in its semantic position, but instead of concatenating its phonetic features, these are held in a waiting position. And when the moving string gets to its landing position, it is concatenated with the main string. So that's the basic idea. Um, and that's what we can see here. The string book is like dragged, if you want, upwards. So we have various non-terminal symbols with dimension 2 carrying like the main string and the moving string, which is book here, here, here. And well, this comma uh, doesn't mean just mean that these are non-terminal symbols with 2 dimensions, but these are like unique non-terminal symbols. And okay, so this goes on like this until we reach like this symbol with just 1 dimension that joins this pair of strings, and at the same time it like merges the n with the relative clause uh, in a similar way as this one. Okay, so what we get at the end is that the semantic relation between the noun and the verb is now local. So they are introduced at the same step of the derivation, so that when we want to do the semantic interpretation, they will be close to each other. These are Clark words, so that the appropriate meaning can be constructed compositionally. Um, okay, so these 2 rules work in the same way. They stick B and W, and they put apart U, which is the moving constituent or the moving string, actually, and until we get here, and they are uh, here, and they are joined. And what we have here and here is like a very common rule, which we will have to use whenever we want a moving constituent. So this rule basically means that we have a constituent with something, I mean, this constituent with something moving out of it within this symbol, this non-terminal. Um, we also have a normal constituent without any movement, and the result is a new constituent where the U is still moving. Okay, and but one problem that Clark points out at this point is that we should define every combination of rules with moving and non-moving constituents, and this may be too large to be plausibly learned. So this is like a problem that Clark raises here. We can also have this alternative with a trace where we define a noun as a pair of strings uh, and actually as a pair of as a pair of predicates of dimension 1, but one string is the trace, which should be like phonetically null, and the other is the string that will be pronounced. And what we have here is that the trace here, I mean, the trace joins the verb and stays here, while the other part of the noun keeps moving upwards. So we can go for this if we want. Okay, so now we can consider briefly the equivalence between MCFGs and 3 adjoining grammars. What we know is that the set of languages defined by TAGs are properly contained in the set of languages that MCFG can define. But TAGs are more restrictive in that they only use well-nested rules like this one, and not this one, because we need rules where each pair of strings don't overlap, but rather are like nested one within the other, like this and like this. So with these MCFGs, I mean, they become weakly equivalent with this restriction that well, Clark poses. And in the case of minimalist grammars, it has been noticed that for every MG, okay, there is weakly and strongly equivalent MCFG grammar. And in order to make the translation between these two kind of rules, we may see the whole set of features here, as the category label. And I think we should include here the one colon or the semicolon. Sorry, one semicolon or two semicolon, meaning that this is a simple tree or a complex tree. If I'm not wrong, this is also a feature that we have to include in our rules. But yeah, that's the key for like making the translation between rules. The features become a unique category label, right? So, for example, these are the inference rules. I think they were first proposed by Harkema, and they allow us to define a bottom-up parser. And here is the yield, here. And what we see is that when a non-mover merges with a mover, like in merge 3 and in move 2, the concatenation doesn't take place, right? We have here a comma, as we saw before, and S and T are not concatenated, so we have a rule of dimension 2 here. We will have a rule of dimension 2, I think, but not in this case. And also we can see that the order of the strings is defined also by these rules, as we saw with MCFGs rules. So if I'm not wrong, here would be like a hypothetical derivation with MCFGs steps on the left and MGs steps to the right. So if we assume that book moves to the specified position of the relative phrase at the end of the derivation, and here the highlighted sequences of features stand for non-terminal symbols. And for instance, if we look at merge 2, I mean, this step is quite similar to the movement rules we just saw. So here I may be seen as W, and read is like B, and book is like U. And what we see is that book is like kept apart from the rest of the string. And until here, until this step, when the licensor and the licensee are like cancelled. So here we have a step or a rule with dimension 1, and these strings are finally concatenated, and these features are, sorry, cancelled. And I think this would be the like the translation, but I'm not really certain about this. I mean, whether the rules that correspond to each step here are established by the parser based on the inference rules here from the previous slide. So I'm not really sure about it, but maybe we can see this later. Okay. So finally, this is how we get the time complexity of a parsing algorithm for MCFGs. It depends on the rank of a grammar, which is the maximum number of non-terminals that we may have on the right-hand side of a rule. And I mentioned D, which is the maximum number of chunks that the predicate may apply to. So MCFGs can be parsed in time n, which is the length of the input, raised to the power of r plus 1 times d. So in the case of CFGs, if we stick to the Chomsky normal form, we have dimension 1 and rank 2. So we have n raised to the cube, and in the case of MCFGs, as the ones that Clark proposes, we have dimension 2 and rank 2. So the time complexity would be n to the power of 6. Okay, so conclusions. MCFGs provide a way of dealing with movement and discontinuous constituents in polynomial time, preserving to a large degree the structural descriptions of traditional generative analysis. And as a consequence, MGs are computationally tractable as well. And of course, this also means that they can be efficiently learned, so they have more explanatory adequacy, which is obviously very important. Um, okay, and this, I think, follows from the above. So MCFGs show that there is not necessarily a technical difference between formalism that use movement and formalism that don't. Um, okay, so but going back one step, so um, here I think it's interesting that we have a formalism in which the syntactic structure is revealed again at the same time at the like phonetic form. So these are like synchronous operation as with uh, categorical grammars, that Stedman's categorical grammars. But I don't think this is the case for all like minimalist versions. For example, the version from Collins and Stabler from 2016, they are like more traditional in the sense that they use a version of transfer to maintain like the phase theory, but well, Stabler's versions are do the both operations at the same time. Of course, we don't have here like a logical form, but okay. So what we also know is that well-nested MCFGs are weakly equivalent to three adjoining grammars and categorical grammars, among other formalisms, which means that the languages generated by them share the properties of all mildly context-sensitive languages, which are basically that context-free languages are properly contained in this one. And they can be parsed in polynomial time, as we saw, and they have linear growth, um, and they can capture some kind of cross dependencies and nested dependencies. And finally, this is what Clark says: this equivalence between MCFGs and these formalisms suggests that MCFGs define the right combinatorial operations to model natural language syntax. Okay, and that's basically it. These are the reference, and well, thank you for listening.